starting right now. If you have questions, put them in the chat and we'll save those for the end, but we'll make sure we get to them. All right, have at it, Jeff.
Great, awesome. Oops, there we go. Thanks, Elizabeth. I appreciate the intro and thanks for the opportunity to come talk to everyone today. Well, I get to talk about snow and lasers, which are two of my favorite things. Any chance I get, I will relish. I'm calling this talk the spatial revolution, and I think as you all are no doubt well aware and well positioned to take advantage of, there's a wealth of new data sources out there. I'm talking mostly about terrain and snow data today, but that extends well beyond this realm to all different modes and sectors of Earth and spatial science. So it's pretty exciting stuff. Today I'll talk about snow hydrology and avalanches and ways that we are developing new tools to enable how we deal with these realms. I am, as Elizabeth mentioned, I am a researcher at the National Snow and Ice Data Center and the Western Water Assessment down at the University of Colorado. And I'm also co-founder of Airborne Snow Observatories, Inc. And I'll talk a bit about that and the research that I do at CU as part of this. So, brief outline. I'll initially and then kind of throughout discuss some of the challenges of measuring snow in the mountain environment. And a bit of why that's important. And then I'll dive into some applications of new sources of high resolution spatial data for snow hydrology, for avalanche mitigation, and also for recreation, some new tools for recreation in the mountains. So I'll start by taking us back in a little time warp here to the 1860s and what has become known as the Lake Tahoe Water Wars. So I was astonished to learn that Lake Tahoe in California was discovered in 1840, which is kind of astonishing given that the gold rush of 1849, 49ers, was only less than 10 years after that. So the fact that this major, huge lake in the mountains of California was basically discovered by westward migrants and settlers that late kind of in the history of California was amazing to me. By the 1860s, there were many canal projects proposed to take water from Lake Tahoe and distribute it to agricultural and other uses in Northern California. In the late 1860s, the first timber dam, this is shown in the bottom right here, was constructed on the Truckee River, which drains Lake Tahoe, raised the lake level a little bit, and perhaps a precursor to modern issues, the raising of that lake level angered some of the new residents building vacation homes on the shoreline up there. Early in the 1900s, the first Bureau of Reclamation water project was conceived and implemented in northern Nevada, diverting water from the Truckee River to this water project for irrigation of croplands in what's now the Reno Sparks area. And in doing so, they overestimated the reliability of the flows in the Truckee River, so that the amount of water each year that they had counted on ended up not being as consistent as planned, and therefore jeopardizing the reliability of deliveries to farmers in that Newlands project going forward. So this political conflict, not only the water supply delivery, but the implications and impacts of water management efforts on the local environment, really demanded a better understanding of the water supply. Enter who we consider the father of snow science in the United States, Dr. James Church. He was a classics professor, so like Greek and Roman literature classics at the University of Nevada in Reno, and in the late 1909 developed this snow tube for measuring the amount of water present in the snowpack at a particular location. And he had this insight that the amount of water at the beginning of the snowmelt season in the mountains around Lake Tahoe could predict the lake levels later on in the summer. And so he developed this instrument and started measuring snow at this location near Mount Rose, which has now become the longest term operational water management or snow measurement in the United States, starting in 1910 and going through current. And he was right. The amount of water stored as snow in the springtime in the mountains is directly related to not just lake levels, but stream flow and river runoff throughout the connected and adjacent regions. And we still use this technique operationally today. Here's Frank Gerke, until recently the head of the California Cooperative Snow Surveys, using what's now known as the federal sampler, originally called the Mount Rose sampler, to measure the weight of the snowpack at that location. We've since added in the 70s and 80s, primarily some automated sensors called SnowTel. That's at the bottom right here. And the main measurement there is this snow pillow, which weighs the amount of snow sitting on it. And this SnowTel network, there's over 800 of these installed around the Western US, which seems like kind of a lot, but then we think about how these data are used. These individual point measurements are used to describe the water content, the snow water content in an entire basin. So here, this map on the right is Huck 6 basins throughout the Western US, colored by their percent of average snow water equivalent, how much water there would be if you melted the snowpack. And this is March of last year. If we zoom in a little bit here to the Northern Front Range, and these basins are colored the same. In reality, these basin colors are derived from a small number of those SnowTel sites that exist within those polygons. So we're taking the conditions at this small set of point locations and averaging them together to display, and there's probably an entire course on cartography that can be discussed with this in particular challenge, to display the basin water content based on that small subset of measurements. And that small subset doesn't necessarily describe the full snowpack all that well. So here is the distribution of elevations of SnowTel sites for each Western state. Colorado's circled in red there. And we could see that the elevations of the SnowTel don't span the entire elevation of terrain within the state. So there's a bunch of terrain higher than the SnowTel network, and there's a bunch lower than the SnowTel network. And even at the margins of that network distribution are pretty scarce. So basically, there can be a ton of snow above and below the network that we don't even see. And that's just the beginning of it. These stations are commonly in specific forest clearing environments. So really, using them for operational water management means that we are assuming that they represent the basin water content and the basin characteristics of the snowpack, when in fact they arguably do not. And that has a direct impact on our ability to forecast river runoff based on those data. So the typical measurement as described in these maps is percent of period median. So in this case, it's 1981 to 2010. We're about to switch and start using 1991 to 2020. But nevertheless, they're characterized by their relationship on this particular date to what it has been on that date in the years in the past. And then we use a regression relationship from how much snow there is now and how much stream flow there should be later in the summer. That is notoriously not that accurate, or variably accurate, I should say. As is shown in this table on the right, this is information from Lake Dillon up in Summit County, operated by Denver Water. And you can see that some years, the April 1st forecast, again, based on, in this case, 4 SnowTel measurements in that basin, in some years is a pretty good indicator of the April through July total basin runoff into the reservoir. You know, if you get down to 2% error, you're doing pretty darn good. We can barely measure stream flow to that accuracy. But certainly in some years, if we're looking at 15, 20, 30, or even 56% error in 2012, if it's your job to turn the knob on the dam, those numbers are not confidence inspiring. And we see this similar variability throughout the state, throughout the river basin, throughout the West. And one of the main reasons is that this technique of relying on the period of record, relying on how current conditions compare to the past, is not that reliable, and it's getting less so with climate change and hydroclimate change. And this describes that a little bit more. On the left shows is a cumulative distribution plot showing April through July runoff forecast errors for the American River in California, basically showing that half of the time the error is around 20%, and in 1 in 5 years that error is approaching 40%. Again, a difficult number on which to base very consequential water management decisions. Part of the reason is what we term non-stationarity. So the hydroclimate is changing, and even in this case, in the Tuolumne River in California, where the mean flow, annual flow, appears to be relatively constant, we're seeing a big increase in the standard deviation year to year. So the statistics of stream flow are changing, which means that if we are forecasting based on those statistics, that is an unreliable methodology. So all this background goes to say there's a problem with the reliability of our river forecasting system, especially considering climate change, and we need a technique to make that water supply forecasting more robust. And one way to do so is to decrease this reliance on the historic record that I was just describing, and to do so by increasing the availability and use of spatial data. Instead of these sparse point measurements that we're using and assuming they represent the full watershed, we use data that cover the entire watershed. And this should allow us to get much more accurate with our forecasting. And so one way we're doing this now is with the Airborne Snow Observatory, where we map these two most critical snow properties to forecast river runoff. And those are snow water equivalent across the entire river basin, and snow albedo, or the reflectivity of the snowpack, which governs the amount of solar radiation absorbed and thereby how fast the snowpack will melt. We do this with two combined remote sensing instruments, a mapping LiDAR, as well as a visible and near infrared spectrometer. And we put these instruments on a twin engine aircraft. We fly them at high altitude, and we turn these products around within 72 hours, such that these data are maximally useful for water management operations. We started this program 8 years ago now at NASA Jet Propulsion Lab, and just recently have transitioned out of NASA to a public benefit corporation incorporated here in Colorado, and where we're basically continuing the same program. So how do we do this? We basically put the plane in the air and start mowing the lawn over the river basin, and thereby achieving full spatial coverage of the watershed. And to get to snow depth and water equivalent, we, in essence, do differential elevation mapping. So we make two elevation maps using the laser scanner, constraining them with the spectrometer to make sure we're only subtracting in snow-covered areas, and to minimize bias, we get a snow depth map by subtracting those two elevation maps, snow-free and snow-covered. Then we measure and simulate snow density, and the product of depth and density gives us that water equivalent, the mass of snow across the landscape. And we have one thing going for us here, and that is that the majority of spatial variability of water equivalent across the landscape comes from variations in snow depth. And so snow density is much more conservative spatially, and we're able to measure and model that effectively. So now we have a 50-meter resolution map of snow water equivalent that covers the entire watershed. And there's a whole bunch of things that can be done with that. One of them is to just add up the entire volume of snow water in the basin and treat that as sort of a minimum forecast. And if we do that in the Tuolumne Basin in Central California, we see this extremely strong relationship between the amount of snow measured from the air and the measured inflow to the Hetch Hetchy Reservoir from that date through the end of July with a 0.99 R squared. And what this means, no matter if it's a super dry year like 2015 or a super wet year like 2017, that once the dam operators have some data from the ASO program, they can have a very, very strong idea as to how much, exactly what the inflow volume to their reservoir is going to be. And that's very enabling from a water management standpoint. They can then manage for water supply, hydropower, and in-stream flows all effectively. One example of how that data has been put to use is in the Kings River. This is the southern end of the map here, Southern Sierra. They have an interesting situation in the Kings where in a flood declaration, so if the official forecasts say that there's going to be a flood, the Army Corps of Engineers takes over the Pine Flat Dam operations and runs it purely to protect the dam, no regard for any water deliveries for the Kings River Water Association. In 2019, the forecasts were showing that there was not going to be a flood, but ASO data was showing that there was quite a lot more snow up there than the official forecasts were recognizing. The Kings River Water Association was able to release water early, deliver water to their constituents, and save room in the reservoir, and by doing so, avoid a flood declaration. And this saved them over $100 million in water costs that year. So improved snowpack knowledge can have real on-the-ground implications for not just the effectiveness of water management, but also the economics of it. So we've been doing this a lot in California, as I've mentioned a couple examples of, and this program is building out with support from the state and water users to build out to regular full state coverage over the next 5 years. So that's not just the Central and Southern Sierra, all the way up through the Northern Sierra and into the Lake Shasta and Klamath basins. So pretty exciting shift in the operational water management paradigm in California. We've also been flying extensively in Colorado. In fact, our first flight ever in 2013 was in Colorado, and mostly project-based funds here for NASA science investigations like the SNOX campaign, but also some support from the Colorado Water Conservation Board and others, including Denver Water for water management purposes. And I'll show you some Colorado data here just to give you a flavor of what these data can look like. This is the East River, so town of Crested Butte here, central Colorado, and this is April of 2019. And the color bar on the bottom right here shows lower snow depths in the blues, going up through yellow to deeper snow in the reds, 4 meters or greater. And at this almost literally 30,000 foot view here, we see some patterns that we might typically expect, that is lower snow at low elevations and greater snow as we go up in elevation. But as we zoom in on these data, we can see that the accumulation pattern for snow is vastly more complicated than a simple elevation relationship. We see imprinted on that lots of wind redistribution, so scour and probably some melt as well on the windward and solar slopes. Big piles of snow where it's been drifted into the north-facing cirques. Lots of smaller wind ripple patterns. And then in this case, lots of avalanche activity, which you may recall in 2019, there was a huge avalanche cycle statewide, closed highways everywhere, et cetera. And we could see this throughout this image. This bluish area here on the slope shows that all this snow, which should be in yellows trending red, has ended up in these big red piles down in the bottom of the stream channel. Once you see that pattern, you could see those all over this map. Really extensive avalanche activity in that year. Another view nearby, this is Schofield Pass, some big avalanches, including this one, which burped some water out of that lake. And so a really heterogeneous snow environment, from very little snow to very, very deep snow over short distances. There's a SNOTEL site actually in this image. It's just on the other side of Schofield Pass over here. And I think just looking at this image, it's pretty intuitive to say that, okay, where would you try to locate a single snow measurement station that can even hope to capture the complexity of the snow accumulation patterns in this watershed? The answer is you probably can't. So as we move into the melt season, here's the same domain, but on the 10th of June. I've drawn the 10,400 foot contour line on here as well, and we could see, and that line is the height of or the elevation of the highest snowtail station in the watershed. So here we are at the beginning of June. There's still a ton of snow left, but nearly all of it is above the elevation of our station network. So we're effectively blind to what the snowpack is doing at this point, even though there's quite clearly a ton of snow left up high. Another way to look at this is slicing those data sets into elevation bands. So the April data is in the blue bands, and the June data is in the see-through orange. And we could see that, yes, by June, most of the snow stations are melting out or nearly so in both the East River and Taylor River. But the upper elevations have maintained or even increased snowpack at that point. So we have no operational data without the airborne measurements to track that change in the snowpack at upper elevations. Similar story across the ridge line into the Roaring Fork Basin. You'll recognize the maroon bells just uphill from Aspen. It's these deep snow pockets that are our stream flow late in the water year. So when the creeks are still flowing in July and August, it's predominantly melt out of these deep patches that drives that, where everything else is snow free. And without the ability to map where those are, we have no idea how much snow is actually in those, particularly in a basin like Maroon Creek here, where there's no station to measure the snowpack. So these data allow us to map not only these fine scale patterns and capture that great complexity in the snowpack, but they let us do it over large areas and capture the entire watershed. One way that we've put that to work here in Colorado is in the Blue River Basin, again, for Denver water. In 2019, we flew a couple times, and particularly the June 24th flight was just as the snow pillows were about to melt out. So 2 days later, no more snow on the snowtail sites, and there had just been a peak in the stream flow shown on the bottom right there. And typically with their operations, when they see the stream flow peak, they close the dam, capture the rest of the snow melt, and save it all for water supply. Well, they could see that there was a ton of snow left on the hills. The ASO measurement showed that there was actually 115,000 acre feet of water left, which ended up being half of the total annual inflow to the reservoir. So they were able to see that number, delay their operations by a couple of weeks, and capture that second, even higher peak in stream flow in the reservoir, and they did so without flooding Silverthorne. So that's an important operational constraint for them. They can't open the dam very much, otherwise they start flooding infrastructure downstream. So great result from them, congruent with our experiences in California as well. And I think really the ongoing work with ASO and water management partners points to a pretty significant shift in how we can measure and manage our snow water resource in the mountains. So it's not just these broad watersheds that demand scrutiny and new measurements. It's also slope scale snow accumulation patterns, and particularly the implications for avalanche safety, control, and mitigation. Knowing how the snow accumulates across the landscape at the slope scale. So we're not talking the whole watershed, we're talking just individual starting zones, avalanche starting zones, or individual runouts. This is critical for proper planning and placement of avalanche mitigation infrastructure, so big supporting structures like on the top right to keep the snow on the hill, or explosives placement or exploder placement. Conventionally, these measures are cited using expert knowledge, so some local knowledge of the terrain and where snow typically accumulates, but we can use this new LiDAR technology to actually measure the accumulation, not just at one point in time, but over time, and really get a feel for how the snow builds up on the landscape. One way that people have done it in the past, trying to get spatial data about the likelihood of avalanche release, is to make lots of manual measurements across the slope. And those early efforts at this were quite revealing of variation in slope stability and the properties of the snowpack across the slope, but they have to destroy the snowpack in order to get these measurements, and therefore they're not really that useful for planning future stability assessments on that terrain. So we've taken to using a ground-based LiDAR scanner, so similar technology to that we fly in the aircraft, but you can carry it in a backpack and put it on a tripod and map the slope scale distribution of snow at very high resolution. I'll show you a couple of videos of what that looked like. This is at Arapahoe Basin, the Montezuma Bowl terrain, and there's a couple of color scales here. We're looking at total snow depth from green to red, and it'll shift to change in snow depth from the prior scan. In this case, on the 17th of January, we can see that it's been mostly snow accumulation that's happened, going into the red colors, and quite a bit of variation in that. And then you could see 2 avalanches that were released by explosives. As we zoom in on that, we can see the surrounding undisturbed snow showing an accumulation from the prior scan, and within the area of the avalanche, the white colors and trending into the greens show us that this avalanche ran on the old snow surface and kind of scoured down into it. With these data, we can do things like measure the avalanche extent or the depth, and then we can look at where those avalanches occurred across the landscape and relative to the snow accumulation. We can track what the ski patrol is doing here with their ski cuts and bomb craters to try to release avalanches in that terrain and make it safe for the public. We can ask questions like, why didn't this big drift release with that bomb shot directly on it? And it's probably because that bomb could have been placed a little more to the edge of that big accumulation of snow. So lots of amazing things that can be done with this newfound insight into what that snowpack is doing. Different part of the hill. This is the east wall again in Arapahoe Basin in February 2014. Same color scheme here, showing the total snow depth, and then here it is showing the storm accumulation, so change in snow depth from the 23rd of January to the 1st. They placed one explosive that took out this entire slope in this avalanche. Again, the color showing that avalanche likely ran on the old snow surface, so the white for 0 depth change, and then scoured down into those lower layers, producing the greens and blues in this map. Again, with the high resolution data, we can do things like map release areas and deposition areas, measure, make some typical measurements of the avalanche run out, like the alpha angle or slope angles of the release area and deposition area. All data that's really hard to come by with just typical manual measurements and with the need for putting a person on foot or on skis out into avalanche terrain to make those measurements. So a pretty cool new way to look at the snowpack, and that's interesting from a science and certainly a gee whiz perspective, but we wanted to take it to the next step and say, okay, how can we use these data operationally? We've used them in near real time to help ski patrol choose locations to place their explosives. And we've also used them to help design avalanche mitigation infrastructure. So this is the steep gullies terrain at Arapahoe Basin, which was just recently opened to the public a couple of years ago. In getting ready to open this terrain, they planned a series of tramways, basically aerial cables, used to deliver explosives to this terrain and release avalanches and make it safe for the skiing public. This is their original tramway design. By looking at a number of snow depth maps made with our ground-based LiDAR, the snow safety team redesigned their tramway network not only to allow easier access for their workers, but to allow for multiple different shot placements targeting the large snow accumulation zones in that terrain. Targeting those zones or aligning the wires to align with those zones was a pretty difficult thing to achieve with just using a visual assessment of the snow there. So pretty cool application of this new technology for planning purposes. Oop, getting the pinwheel of death here. Come on. There we go. Just over the hill this is the Seven Cisterns avalanche path on Highway 6 and Loveland Pass. And here we're working with CDOT to assess the effectiveness of their new GAZEX system. So they put in a bunch of exploders shown in this image with all of these different pins. For some reason, my video is choking here. This is not good. Here we go. Okay, so each pin represents the location of an exploder, and they wanted to know how effective using these things was being in removing the snowpack. Here's an example of one of them being fired. You can see the exploder tube up here in the top of the start zone. There's a couple more over to the right. And here that explosion has released a pretty good sized avalanche. The highway is down here just hidden by the trees. And we can see the snow pile or the avalanche hitting the highway and bouncing over it. So pretty good result from that release. And then we can go in with the same and do another LiDAR scan after they do their avalanche control and see what part of the starting zones has been cleaned out with those explosives application. And in this particular case, they shot all of the exploders, and we can go, step by step across all these avalanche paths and evaluate just how well they've done. For the most part, cleaning out the entire slide path in each of these, with the exception of the sister number 6 here, which had just a little bit of a slough that reached most of the way down, but there's still quite a bit of snow left in that starting zone. So interesting application here for spatial snow data for evaluating the effectiveness of infrastructure. So in my last, I don't know, 10 minutes here, I'll talk a little bit about how these spatial data can also be used in a recreation context, and with the users being, us, not the folks in charge of the highway or the ski area or the water management, but actually putting spatial data and terrain data to work in our recreation pursuits. And so in recent years, there's been a development of lots of different digital tools for backcountry route finding and navigation. Mostly I'm talking about this again in an avalanche safety context, but these data are useful for all kinds of backcountry recreation, and whether it's on foot or mountain biking or anything. And these tools are super cool. They're basically pocket GIS systems where you can have in your smartphone a bunch of different GIS data layers. And some tools designed to exploit those layers, like planning and tracking, linkage with other online resources and guidebooks, et cetera. So there's been a proliferation of these type of tools, and you could do really cool things like these, like plan a route across your desired terrain or desired hiking or skiing area, and get information about how steep the terrain is there, what your maximum slope angles are, what aspect it is, tree cover, whether you're going to be on private land, etc. So pretty cool, every man's GIS system. The challenge becomes, and those as you are GIS users, you understand that it's really important to know where the data come from and their levels of accuracy when you're putting them to use. And that raises a couple of kind of key questions for deployment and use of these tools. Are we making accuracy assumptions when we're using these digital mapping tools? I think you could see my answer for that is yes. And can we converge on some best practices to use these tools most effectively and safely? So as you're aware, the way we interact with elevation data has evolved with technology and with those data sources, from sort of quasi quantitative methods of display like hashers, commonly seen on kind of throwback or historical maps now, to contour maps, to what we're more used to these days, digital elevation models, and products derived from those. And really the fundamental data source for enabling all of these tools is the digital elevation model. And breaking that down as to what that is, I think can be a bit instructive. It's digital, of course, stored in an electronic source. It's elevation, height above a reference elevation. And most importantly, it's a model. It's a spatial representation of the landscape, in most cases on a regular grid. Obviously, there are other ways to display that. But the key point is that it's a model. All models are wrong, but some are useful, as the great statistician George Box said. And the key then is to say, okay, if we know how the model is wrong, then we can apply it in the most useful manner. So these digital elevation models are created in many different ways depending on the data available, and that's changed over time, from stereophotogrammetry of actual print photographs to digital photogrammetry these days, or radar interferometry, or LiDAR elevation mapping. The common thing to all of these techniques, no matter how rudimentary or advanced, is that we start with some abstraction of the land surface and refine it to pull out elevation information. These data are pretty ubiquitous, of course, the most common example in the US being the National Elevation data set. And large portions of that data set were actually derived from physical paper maps that were built from stereophotogrammetry. So in this case, overlapping aerial images of the same terrain, showing the same terrain from two different look angles. Those get put into this wonderfully steampunk looking machine called a stereo plotter. And this poor guy sits in a dark room for hours at an end, tracing lines of equal elevation or contour lines on these stereo photo maps to produce a paper contour map. Those maps in the 80s and 90s started to be digitally scanned, interpolated to a 30-meter DEM. Those 30-meter DEMs have since been refined, filtered, and reinterpolated at 10 meters. And that's the common national elevation data set product that you can go download from the USGS as a digital map. So that digital map source came from analog photographs and manual interpolation. Contrast that with some of the modern maps derived from LiDAR or from satellite stereo photos, where we can get 1 meter hyper accurate elevation even under the trees. And you could see that without knowing where this DEM information came from, that a user might be inclined to misapply the accuracy there. Because there's different error sources and different methods of measurement, the different types of errors we can get in DEMs vary by location and vary by the data source. So we can have biases, systematic or otherwise. We can have correlation errors, and all of that depends on what's being measured, how it's being measured. And none of this is particularly obvious to an end user. Even an advanced GIS analyst has to do some digging and have some base level understanding of how the data are produced in order to understand these biases. And that results in some global estimates of the error of these various data sets, but at any individual point, those errors can actually be much greater. One recent example of this is a paper in 2018 that recalculated sea level rise impact estimates using a different elevation source. So previously, they were using the shuttle radar topography derived global elevation data set, and that radar instrument actually sees the top of the trees and the top of the buildings, not the ground surface underneath. So in low-lying terrain like Charleston, South Carolina, or Bangladesh or Bangkok, if you're mapping the top of the trees versus the actual ground surface, your estimates of the impacts of sea level rise are going to be dramatically incorrect. By using LiDAR revised coastal DEMs, they greatly expanded the estimated inundation areas under various sea level rise scenarios and increased the at-risk population estimate globally from 250 million to 350 million people. So there's a real world implication of the nature of the remote sensing instrument used to derive the elevation data set. One of the implications, particularly for navigation in rough terrain, is derivation of terrain metrics like slope. Slope simplistically is the rise and run between elevations. In a gridded DEM, that's done by solving for using a neighborhood algorithm to look at the adjacent cells and calculate a slope gradient for each cell, with the magnitude of that being the terrain slope and the direction of that vector being the terrain aspect. We're all used to doing this with one click in whatever GIS package you prefer, but it has implications for our ability to use those data because DEM-derived slope angles are prone to errors, both in the DEM, but also from effects of DEM resolution. So we can see some schematic profiles on the right with the different columns show the different grid resolutions, with the black trace showing the true elevation profile. And if we draw lines connecting the center of each of those DEM grid cells, we can see that we're missing the highs and lows in the terrain and underestimating slopes with those coarser DEM elevations. And so that can have a dramatic impact if we're actually looking for something that depends on slope angle, like avalanche release. So here, if we look at some oblique views of some terrain in central Colorado at 10-meter resolution and 1-meter resolution, it's pretty obvious which one is a more realistic depiction of the terrain. But when we put slope angles derived on there, and then maybe try to plan a ski route through that terrain, if we plan that route based on a 10-meter resolution DEM, but then look at it on the 1-meter, we can see that we're actually exposing that route to a lot of smaller, steep terrain features than are evident in the 10-meter DEM. This is just one example of how one might be led astray by coarse data or data that of an unknown provenance. But I think it's a pretty easy one to anticipate with unskilled users putting these data to work. One sort of recent development is the proliferation of high-resolution LiDAR data. So these 10-meter topo map derived elevation maps are slowly being replaced by 1-meter LiDAR data across the US. And from the recreation standpoint, does this change the game? Does that really remove the need for the end user to have a deeper understanding of where their data is coming from? I would argue no. It just changes how the interpretation that needs to be made, and really this is probably too granular for this talk. This is specific to an avalanche problem, but I think it really raises an interesting question, and that is how users interact with data, and how can we design tools that don't rely on a deep understanding of the data production and data curation process in order to be used effectively. So the avalanche recreation world is converging on some best practices for using these tools, and how those best practices shift over time. But I think it's just a fascinating intersection of technology and mapping, along with this sort of social connection and end user communication challenge. I think it really neatly encapsulates a whole bunch of challenges that are front and center in the GIS world these days. So in summary, I think this is a pretty exciting time to be involved with spatial data. The spatial revolution, as I like to call it, is ongoing. We're living it in real time. We're moving beyond science into real world applications, and enabling physical models of the land surface and of Earth systems that were difficult to run effectively beforehand. We're seeing resilience being built into our forecasting and management systems, from water supply and avalanching, as well as brand new tools for lesser skilled users. So pretty exciting stuff. Thanks very much, and I'm happy to take any questions if I left myself any time here.
Thank you so much, Jeff. I'm going to unshare so we can see each other again. We do have a bunch of questions, so I'm gonna start in the order that they were given, but we do have a couple minutes. If you can stay, Jeff, we can keep talking, and then if anyone has to go at 4:50, you can go. Okay, first question from Serena. Are there any positive outcomes to avalanches, or is it all bad, or is there some good in there? Water supply or anything?
Yeah, so there's some really interesting questions about what avalanches do hydrologically. And that's something that I actually have a new grant to study, and I'm going to use that 2019 data set from the Upper Gunnison River to look at. So basically, you're taking a huge mass of snow and you're putting it at a lower elevation, but you're compacting it into a smaller volume, so the surface area to volume ratio changes, and you're making it more dense. So does that make it melt faster? Does it make it melt slower? What does it do to the slopes that should have been covered deeper in snow later in the season? We don't really know. We have some decent ideas of what may happen there, but I think the hydrologic impacts is definitely a curious one, and it may actually delay melt later into the summer season and preserve stream flows. That would be a pretty interesting result. As far as human interactions with avalanches, it's rare that those are positive experiences. Recent events, I think, speak to that. There's been a whole bunch of avalanche deaths in Colorado and around the West just in the past week. So be careful out there, people. Hopefully, the tools that I've shown a bit here are helping operations that deal with avalanche mitigation increase their safety margin, and hopefully proper application of those digital navigation tools can help as well.
Great, thanks. Next question from Mo. What's the future of the SNOTEL sites? Is LiDAR data being used similarly in other continents?
Yeah, great. So the SNOTELs will continue, and we need them to continue. They are important measurements for tracking the snowpack long term. They provide data hourly versus the fastest repeat we've flown with the Airborne LiDAR is weekly. And we also use those data. We need the measurements of snow depth and the snow water equivalent at the SNOTELs to measure snow density, which allows us to convert from snow depth to snow water equivalent. So we see the SNOTEL network as critical, but we're envisioning and applying a new use for those data, one that doesn't rely on stationarity in the period of record. We've had a demonstration project of ASO in Switzerland and some ongoing development in Norway and New Zealand and Austria and France and Chile and India. So pretty rapid adoption of this, or at least demonstration of it globally. Pretty much anywhere that people rely on melting snow for water, this can be applied.
Next question from Mitchell. Are the data presented in that video of Montezuma Bowl gathered from a ground-based LiDAR?
Yes, all of the Arapahoe Basin data was from that tripod-mounted LiDAR that I showed a picture of. As with the Airborne, we needed to go out in the summer and get a snow-free elevation data set and then come back. And with the avalanche stuff, our general mode is we try to go get a pre-storm map, and then a post-storm map, and then a post-avalanche control map. So that allows us to say, okay, how much, or to map the distribution of new snow from the storm, and then from that assess the effectiveness of avalanche control as well.
Great. Next question, do the explosives have a negative effect on the vegetation and wildlife?
Good question. I don't know directly. Certainly, wildlife don't like big explosions. I can't imagine it's a positive impact. I'm not sure that anybody's ever quantified it though in any way. It doesn't really affect vegetation so much, except in cases where they're applied near trees. But for the most part, that's not the case. So mostly I would be curious what the wildlife impact is.
Next one, and you kind of touched on this when you were talking about how SNOTEL sites are still needed to get SWE values. But the question is, what kind of data or algorithms does ASO use for snow density to convert depth to SWE? Yeah,
so we use measurements from the SNOTEL and also snow course data, so the snow tube, manual snow tubes, where those are available. We also go make manual measurements ourselves as a part of that. But we run a snow model called iSnowBal, which is a 50-meter resolution distributed snow dynamics model. And we constrain that model with the snow depth measurements from the LiDAR. So that combined with the ground-based SNOTEL and snow course measurements keeps that model pretty tight on snow density estimation. And so therefore we have a spatial snow density map that we can multiply by the spatial snow depth map to get the SWE map.
All right, thanks. We have a couple more. Next, are there limitations or biases with the model related to land cover type, like treed versus open?
Yeah, so well, I'll talk about the model and the LiDAR. So there are greater errors under the forest canopy and in steep terrain with the LiDAR compared to flat, open, unobstructed view terrain. From our ground truthing work, we've seen that it's still on the decimeter scale. 10 centimeters are usually better. Most of those errors are normally distributed statistically, which means that if you average them and coarsen your gridded data set, then those errors get diminished. So when we average from 3-meter snow depth to a 50-meter snow depth, that snow depth error basically goes to 0. Our snow cover model, iSnowBal, we haven't really, because we are sticking the snow depth map straight into the model, that's really the only thing that we can use to evaluate it spatially, other than manual density measurements. Those are pretty difficult to get at any great spatial extent. So I would say the model density bias across the landscape is not super well captured, but from what we can see, it's in the single-digit percentages from the data we have been able to collect.
All right, thanks again. Two more. One, since these are all students, do you have general advice for finding jobs or internships?
Yeah, so we have a couple ideas. We have an internship program at ASO Inc. You can find that on our website. Send us a note that way. And more broadly speaking, beyond my own company, there's often opportunities out there for that type of internship, and I recommend just approaching companies directly for that. Often the school or the department will have some information on that as well. Otherwise, and this is with my research hat on, finding out what various faculty, research faculty and teaching faculty are researching can be a great way to learn about different opportunities there, both for getting involved in research projects while you're at school, but we all have our connections beyond the university to other academic institutions and companies. So really it's a networking exercise in its essence. but you have lots of resources available.
Great. And Eric, that was your question. If you want, I can connect you with some of the watershed faculty since you're not in that department. So just drop me an email. Aylin had a question. Is there any capability to tell something about the quality of the snowpack in relation to avalanche danger from LiDAR data? For instance, things like faceting and persistent slabs.
Yeah, that's an interesting question. There's some folks at Montana State who are trying to do this with the same instrument that we've used at A Basin. It's difficult to tell anything about the internal structure of the snowpack since we're getting the return signal is from the surface. Now that said, snow has some pretty interesting and unique reflectance properties, and it may be possible to extract some estimate of grain size or grain shape from the surface reflectance properties with the LiDAR. Active subject of research there. One thing that we do, again, with ASO is since we're flying the spectrometer at the same time, is that the spectrometer can retrieve snow grain size quite reliably from the snow surface. And that combined with the LiDAR data can be pretty interesting for modeling surface energy exchange. One thing that the NASA SnowX campaign is trying to do is to add other instruments to the mix. So in addition to the ASO package, they are trying a bunch of different radar systems that do penetrate the snowpack, and depending on their frequency can see things about the internal structure of the snowpack. And that technique can be particularly powerful when combined with LiDAR snow depth measurements. So some cool science to come out of that SnowX campaign.
Yeah, it sounds like that's a big potential for some research opportunities.
Yeah.
There. Maybe someone's master's someday. And then the last question is from Eric, and I'll let him chime in. He says, insider information on what is the best ski resort. So you'll have to elaborate on what you mean by best. The one that you'll least likely die in an avalanche in?
Well, perhaps. I don't know. I was just sort of laughing. I've been skiing a bunch, so I was wondering what your thoughts were on that.
Yes. Well, I'll answer that two ways. One is that I like to ski really steep terrain, so I like A Basin or Crested Butte or Taos, etc. But being a researcher who works with ski areas, and this was true of my master's degree as well up at Bridger Bowl, I love ski resorts that are interested in learning more about about the environment in which they operate. So for me, that's snow science and avalanches, and I've been privileged to work with ski patrols with that that have that interest and flexibility to work with researchers, but that extends beyond snow science as well into water management and social engagement as well. So I like ski resorts that are invested in their community and in their applied research.
Awesome. Well, again, Jeff, thank you so much. This was fascinating. I think we had a huge group. We had as many non-students as we had students in the actual class here, so that's great. For
Awesome.
Those of you who are still here from the class, don't forget you have to do like a write-up for this. There are 6 speakers. You have to do 5 write-ups, so you're allowed to skip 1. So don't forget to do that. And yeah, again, thanks, Jeff, and everyone have a great day. Have a great evening, and if you go in the backcountry, stay safe.
You're here. Thanks, Elizabeth.
All right. Yeah, thanks, Jeff, so much.